In this video, I'm going to go over Unit 5, Target 1, which is qualitatively analyze systems, applying the fundamentals of momentum and impulse, including the vector nature of both. So let's start with momentum. What is momentum? Momentum is mass in motion. It's just mass in motion. That's conceptually what it means. For the equation, P is the variable we use, and it's just the mass times the velocity. I put vector arrows over the momentum and the velocity variables because it is a vector, it has direction. The direction of the momentum is always the same as the direction of the velocity. Momentum by itself isn't that interesting. Where things get a little bit better, more interesting, more exciting is with impulse. So impulse is just a fancy word for change in momentum. All it means is change in momentum. So we can write impulse in a bunch of different ways. We can write it as delta P, so change in momentum. But what's going to change? If we change the momentum of an object, the mass is really not going to change. You really can't change the mass. If you think you're changing the mass, you're really either changing systems or there's an outside force on that system. So mass isn't going to change what the velocity is. So we can also write it as the mass of the object or the system times the change in velocity of the object or system. Change in velocity is just final minus initial, so we can write it n times v final minus n times v initial. Remember this minus sign in here. A lot of times students miss that. Lastly, when we're talking about impulse, a lot of times we go to a completely different equation, which is the force on an object or a system times the time that force is exerted for. There's also another variable that I don't think shows up on your equation sheet, but you may see it later, which is J for impulse as well. All right, so momentum is mass in motion, impulse is change in momentum. So let's look at this change in momentum. A really common scenario is you have a ball and it bounces, or you have a lump of clay, pretend this is a lump of clay, and we drop it and it just hits the floor and does not bounce. And we ask, like, which one has a bigger change in momentum, or which one experiences a larger impulse? And typically students want to say the bounce, and sometimes that's true and sometimes it's not. If you're trying to memorize things, do not memorize this. This is not something where bounce is always more. So you have to think through it. And the way I want to show you to think through it is with a number line. So for instance, let's say we have the lump of clay or we have the eraser, pretend the eraser and the tennis ball have the same mass. And let's say when it hits the ground, it's going 2 meters per second and it sticks there. So the eraser starts at 2 meters per second and ends up here. So if we look at this on a number line, the fancy arrow here, 2 meters per second to 0. We'll call downward positive for this. So the change of velocity was 2 to the left on our number line, or -2. Now the ball bounces, notice it comes back up. And so let's say it was going 1 meter per second when it came back up. So the ball started at 2 meters per second going down and ended up coming back at 1 meter per second. The most common wrong answer is to say that was a change of 1 meter per second. But that's wrong because it started in a positive direction, we'll call that down, and ended up going in a negative direction. So the change in momentum, while the change in momentum for the eraser was just 2 on our units here, our scale here. The ball went from +2 to -1 for its velocity, and that's a total change of 3. So when you are asked which has a bigger impulse, what's the bigger change in momentum, think about this number line and think about what's the total change. Where did it start? Where did it end up? Don't just look at the two numbers. So for instance, +5 meters per second to -5 meters per second, that's a total change in velocity of 10 meters per second. So you've got to be careful. A lot of students think that's 0, but the direction really matters. And so that's why we included in the target here, including the vector nature of both, because the direction really does matter a lot. So conceptually, you can think of this number line. Also, there is we can think of this graphically. And for instance, if we have there's 2 situations. One with a lot of sports where we want to speed something up. So maybe we want to hit the tennis ball as hard as we can. So we want to give it the biggest impulse possible. So to do that, we want to maximize 2 things. We want to maximize the force and we want to maximize the time. This means if it's a tennis ball, hitting it as hard as we can, and following through for the longest amount of time. Another option we can have, or another scenario, is slowing something down. So for instance, if a car is stopping, you can't control how fast that car is going initially. It's just, it's going 30 miles an hour initially and it's stopping. What's fixed is its change in momentum. So when you're slowing something down, the left-hand side of this equation, or actually kind of the whole equation, the value is just fixed. There's a fixed impulse. And so it's always coming, if we come back to our number line here, we're always going to end up at 0 for, whoops, I missed it. 0, there we go. For the fixed impulse situation. So we're bringing something to a stop, and usually we want to not break something. So it's a egg toss, a water balloon toss, something where you're braking in a car and you don't want to break your car. So the change in momentum is fixed because it's coming from somewhere and it's going to 0. And to make it so it's the easiest sort of landing possible, what we want to do is we want the smallest force, because you don't want to break that egg, and that's going to mean a longest time. So for like an egg toss, you have the egg coming in. In football, they call it the stone hands versus soft hands. And so soft hands would be you're cradling it in. You're exerting this force over a longer period of time, so it's a smaller force required. But stone hands, you're just holding your hands, and it's just hitting, and it's stopping it very, very quickly, short amount of time, so you need a much bigger force. And then graphically, what we have here, we can see, we'll do stone hands in red because it hurts. So stone hands, there's no force, no force. All of a sudden, you start stopping the ball really, really quickly. And so it's a really, really big force. And soft hands is green because it's a little bit better. And you're going to catch the ball, and it's going to be over a longer period of time, so it's not going to be nearly as big of a force. So with soft hands, our time is a very long time and a small force. So here's the force for soft hands and the time for soft hands. While with hard hands, or stone hands, it's a big force. So it's a really, really big force up here. But that force goes over a short amount of time. So there's conceptually two different impulse scenarios that you'll most likely see. One last thing from this graph. The area bound by the graph gives the change in momentum. So force times time is change in momentum. This is a bit of an approximation, but force times time sort of gives us area here. We really need calculus. But if we were to add up all the area under the green curve and compare that to all the area under the red curve, if I did it correctly, they would be the exact same area if it had the exact same change in momentum. So you stop the ball that was going 10 meters per second, and you stop it, and you stop that same ball again going 10 meters per second, but you just stopped it with soft hands versus stone hands. So same impulse, but different force. All right, so there's an overview of Target 1.